Okay, welcome back everyone. We talked about spatial data structures to do more efficient and faster ray tracing and faster intersection tests or less intersection tests. And what we do here is basically a divide and conquer approach. We divide the problem into sub-problems and then we combine them in a conquer step to get the final solutions and sub-problems that are easier to solve or faster to solve. And for the object partitioning, what we do is we divide the space into bounding boxes. That is, we divide the space based on the objects. But of course, we could also divide the space just divide the space itself independent of the objects. So we could do, for example, a uniform division of the space by just putting a uniform grid over it. So imagine that these are all parallel lines, like a parallel grid or a matrix that you have here. And then of course we could also do, in the same way as we tested the bounding boxes for intersections, we can just test the grid cells here. So the approach seems pretty much the same. The difference is, of course, we do this separation now based on just the space independent of the objects, which as a result also means that the objects might cover different grids, but for the intersection test, that doesn't really matter. It's clear that this works in the very same way. And this approach is the very simplest case of it. It's called the uniform spatial subdivision. Uniform, of course, because we make a uniform, uniform division of the space in a way that each cell that we divide it to has the same size and the same shape. And so we get a regular grid, and the good thing with this uniform spatial subdivision is that there is very easy to traverse this grid. For example, if those shapes, those grid cells are indexed, if we have an index, a line and a row index, that we can traverse it like we did with a matrix or with any kind of two-dimensional array that we have, then we just can say, if we start here in this cell, we just have to see at what side the ray exits the cell. If it exits it to this left side, then we just increase, if the index is ij, I is the line, j is the column, we just increase it the j by 1. Here again it exits to the left, so we increase j by 1. Here again it exits to the left, here to the left, so we increase j by 1. Here we see we exit not to the left but to the bottom, which means if this is 0, this is 0, 0 in that case, when I'm saying plus 1, then of course we have to make a plus 1 here for the I. So this is I here, and this is j. So you see here we just need to check at which side we exit, and if we, for example, exit directly at the corner, then of course we have to increase I and j, but you see here that we get the line equation, or the cells that not the line equation, the cells that we need to check based on this line equation, based on the direction of the ray, can be calculated very easily in that case. There's one thing we have to be careful when we do then the actual intersection test in the cell, because we have this situation here that, like I said here, that the objects may intersect with multiple cells. We have one case that can happen, for example, if we have a cell like this and a ray like this, and we have an object here and another object here, then we have first, of course, an overlap here. So we do an intersection test with that cell that contains parts of this object. So if we check if that ray intersects with that object, we get a positive result. So we would stop here and deliver this object as the first one that is hit by the ray, which is wrong because this is the first one. But we do not check that because we already stop here. So we have to be careful when we do the intersection test that we only check it for the t values. This was t y max and t y min here at the bottom, and also for the x it's the same way. So we just have to make sure that the intersection value the intersection point that we get here has a t-value that matches the cell we are currently checking. If that is the case, then it intersects in that cell as the first, so that's the first object that intersects. If not, there could be another object in the way that blocks the view, so we have to be careful to solve that case. But other than that, this is a very simple approach to do this intersection test. But of course, it is not always the most efficient one. Similar to the bounding boxes, where I said we have this, or I gave you this simple example. You have 100 objects here and 100 objects there. So it would be good to have one big bounding box covering those 100 objects and one big bounding box to cover those 100 objects. In the same way, it would be good if we have a regular grid to have a huge grid in the center, but a small grid here where we have all these 100 objects. So it would be good to have a non-uniform distribution of the grid, which is more finer granular in an area where we have more objects and less granular in an area, or bigger in an area where we have minor objects. And the most common approach, or one of the most common approaches to do this, is so-called octrees, which is just a straightforward generalization of 3D generalization of a quad tree, which is the 2D case of an octree. But since 2D is easier to draw, I will just explain the quad tree. But it's the octree is then just going from grid cells, from squares or rectangles to cubes. But other than that, it is really the very same thing. So the idea of the quad tree is that we want to make a non-uniform distribution of the space, non-uniform based on how the objects are distributed in our space. And how we do that is we start with the very first bounding box that contains all the objects. So the smallest bounding box that contains all the objects. And then we know, of course, if the ray doesn't hit that box, it doesn't hit any of the objects. But if it hits the box anywhere, then we have to check all the objects within that box if they might intersect with the ray. So we want to have a finer separation of the box to do first individual tests to see the region where the ray might intersect with objects, or to get those objects in the region of the ray to reduce the number of intersection tests. So we do this by first splitting the ray, the space in a regular uniform way by just making one split into 4 subspaces. And then we say, okay, this is still too big, so we want to have it smaller. We want to have it so small that we say there are maximum 2 objects within one grid cell. So we say, we see here that there is only one object here, but there are more than 2 objects here. So we do a further separation of these others. But we do not a separation here, because we see here, if we would do a further separation here, and if we do an intersection test, we will only increase the number of false positives. But there is no need to further separate this, because we just have one here. So if it intersects with that box, we have to check that object. That also happens here. So we're not increasing the number of tests here. We're only decreasing the number of tests by not making this separation. On the contrary, we're increasing the number of tests, and we're most importantly increasing the number of false positives, which we want to avoid. So we do not make a separation here. We just separate those other cases. And then we see here there are much more cells now that have less objects. So we don't need to do a further split here. But the others here, they have still 3, 3, and 5. So we still want to do a separation here. And now we see all our cells that we have a maximum of 2 objects. So the final condition we wanted to have, we said we want to have maximum 2 objects in one cell, is fulfilled. And we see we have a non-uniform grid that better matches the distribution of the objects. So for example, in this area here, or here where we have more objects in a smaller range, we have a finer grid, whereas in this area here where we have only one object in a larger range, we only have one grid. So by having a larger cell here, we reduce the number of false positives. Good, and of course the traversal now is relatively similar to the or almost similar to the case of the uniform grid. We shoot array, and then we start at the first cell, we check that one, then we check that one, then we check that one, then that one, then this one, then this one, and this one. But of course, it's a little more complicated because we cannot just increase or decrease the index of the cells, because these cells don't have such a uniform index, because we have cells of different sizes. So the traversal is a little more complicated, but it better matches the object distribution. So if you have a more complex example than this one, this is a very simple example. Also, of course, this example just has points as objects. In reality, we have more complex objects, or at least we have triangles, which then, like I said, can overlap between two cells, and then we have to make sure that we also check for this case here, for example. But so you see, the intersection test is a little more, the traversal is a little more complicated in a uniform space, but because the space matches better the distribution, this is usually faster and better. But of course, I said it's usually faster and better, but it doesn't match all cases very well. So for example, if we have a case where we have a lot of objects here and a lot of objects here, it would be better, of course, to map those together into one cell. Now, making these cells like this that are not axis parallel is, of course, kind of more complicated and requires more calculations than have axis parallel cells. But having cells that are not squared but more a rectangular shape might, in certain situations, be better. So, for example, it might be better to have shapes like this, instead of just having these rectangular squared shapes. So also have rectangular shapes, and this is approached with this can be done with an approach called binary space partitioning trees. So the binary space partitioning trees work in the following way: we start with the whole space, and then we, like in a previous case, we split and split until we have cells that only contain a certain amount of objects. In this case, we said 2. So we start by making first a vertical split. So we say we split it in an equal amount, each cell in an equal amount of objects. So in this case, we have 18 objects. So we split it in a way that we have 9 on the left cell and 9 on the right cell. It says here more or less equal size, because of course, if the number is uneven, then we have a difference of 1. Also, because we make an axis parallel split, it could, for example, of course, happen that we have cells like this here, where we have a situation like this here where we have 4 objects. But if this is axis parallel, then we have here, of course, 3 and 1, or the other way around. We have to map those to one of the cells, so it is more or less equal size. We have to do special treatment in these cases, but the idea is to have 2 almost equal sizes. And then, because we want to have something like this here, where is it? Here. Like these rectangular shapes, we switch to split not vertically but horizontally. So we constantly switch between a vertical and a horizontal split. So we look at these 2 subspaces, and now we split them horizontally. So we see here we have here 4, here we have 5, here we have 4, and here we have 5. So we split them in this way, and you see now we're already getting a non-uniform or non-squared parts, non-squared subspaces. And then again we have 4 subspaces which have more objects than our condition, which is maximum 2 objects. So we do again a split. Now we split again vertically. So we have here 2, 3, 2, 2, 2, 3, 1, 3. And then we see here these here already fulfill our condition. So we don't have to do further splits here, but we do further splits with the 2 others. And now we have a situation where all the squares, where all the points, where all the cells have maximum 2 objects. And we see this is a distribution. Now this is a very simple example. It's not as impressive as, for example, if we have this here, then of course we would have something that is much more convincing in the end. the cells that we have if we apply this approach. And but I wanted to use the same example as I used before to illustrate the differences between the approaches. And you can imagine, depending on the distribution, of course, one approach is might be better in one situation, or another approach in another one, depending on the distribution of the actual objects. So like in all the cases when we apply these heuristics or these advanced approaches, it is always difficult to, it's not always straightforward which approach is the best one in a given situation. It is actually a good exercise, and I think it's actually part of, I'm not sure if it is with this or with the bounding boxes. One of the exercises on the tutorials is about think about special cases where one approach works very well and one situations where it doesn't work very well. So this is, I think, a good exercise. There's a question here. It's just a number you have to set, and 2 is just a good compromise. In such a simple example, you would split to 1 because, yeah, there are not that many splits. I mean, in this case, there are not many. There's not a reason to split at all because the calculation wouldn't take much longer. But if you have like really a large space with hundreds of thousands of objects, then of course, depending on how much you split, influences your calculation time. So that is the trade-off that I related to the trade-off I said before. How well are we modeling our space, or how well are we putting our bounding boxes around the object? Makes the intersection faster, but it makes the modeling or the splitting more complicated. So this is the trade-off. We just have to decide it. Yeah. So, but the 2 was just chosen here as because it works nice for explaining. Good. Okay, so now we know how to split a space, but of course the traversal here is more complicated than in the other 2 cases, which is why we usually use, and here the name BSB tree comes in, why we usually use a tree to represent the structure, and that way we can do the intersection relatively easily. And this BSB tree is created based on this separation the following way. We did the first split here with this line. We split it just in 2 halves. So we make this half the root of our tree. So the nodes of our tree are always representing splitting lines. In a second split, we split in that direction here. So this is the splitting line B1. This is B2. We represent splitting lines to the left or below another splitting line as a left subtree. So we have here in a left branch B1. In the right branch we have B2, and then we did another split here, which is C1, C2, C3, and C4. And then we, like I said, the left is always the left subtree is always splitting to the left or splitting up, depending if we do a vertical or a horizontal split. So that is C1, C2, C3, C4, and then we did just one more split here, which is here D, let's call it D2, although it is the first one, and this one D3, because then, no, why did I call it? Oh no, I forgot one, sorry, that's the problem. D1, D2, D3, and then we have here, this one goes here to the right. I should look more at my notes. D1, D2, and D3. So again, we have to be careful if we're splitting horizontally or vertically to make sure that the left ones are always, that we know which one to put to the left and which one to put to the right. And then for each cell we have only the object, so we can write our leaves here, which are the objects. So if this is object 1, 2, 3, 4, 5, and so on, then we get here 1, 2. Here we only have one object here in the left branch, but in the right one we have again 2, 4, 5, and so on. Here, but here we just have objects, so we just have leaves in our tree. So this is of course an easy way to represent it. But most importantly, it is of course an easy way to check the traversal. So for example, if we have a ray that we start shooting here in that direction, then we see it intersects with the right side of A. So we know it doesn't intersect with the left side, so we can ignore that branch, but we explore this area here. And then we see it intersects with this part of C3, but it doesn't intersect with this part of here. I've drawn the ray differently than I did in my notes, so that's why I'm a little confused now. It intersects with the left side, so we go here, but it doesn't intersect with the right side, so we can ignore this part. And then we come... What did I do wrong? No, wait. It intersects with both sides of B2. We're checking B2 first here. I have to look at the notes, of course. We check the node. It intersects with both cells to the top and to the bottom. So we have to go, of course, in both subparts. And then we see here it only intersects with the left side. So we only have to explore this part, but not this part. But then we are at the bottom of our tree, so we do the direct intersection test with these two objects. We see it don't intersect, so there is no output here. On the right side, we have to check both sides again here, because it intersects with both cells here that are created by D3, by C4. So we go in both directions, and then we see here there is no intersection with the leaves, so also no output here. And here we see there is an intersection with this object, and I have to be careful that I'm not crossing this line here. So there is one output here, which is, if this is object, I don't know, let's call it 6 and 7. Then we have here 6, no, but 7, yes. That is our intersecting object. Good. So you see, it's just a tree traversal, but that way we can reduce the number of tests significantly by cutting off parts of our tree. Good. So this is the last fast ray tracing space partitioning algorithm we talk about, and this is actually the one that is, I think, most important for gamers or for game programmers. The octrees are something that is very often used in game programming, or the quad trees in 2D. Are there any questions about this? No, because that concludes the ray tracing part, which means it also concludes most of the course. I only have some final summarization remarks. So first of all, to wrap up the whole thing, I mean, I said at the very beginning that I think this course, the actual content of the course isn't really that difficult. It's more the amount of information that is in this course, and also the theory and the practice that makes this course quite difficult. And I guess most of you understand now, or believe me now, if you didn't do at the beginning, because we actually covered quite a lot in the book. We covered the first 13 chapters, almost the first 13 chapters, which is, I think, chapter 1 to 8 is considered the basics of graphics, and then the other topics are considered advanced topics, although I would, for example, say texture mapping is still a basic method, although it is listed in the advanced topics. I didn't cover the third one, which is raster images, and the ninth one, which is signal processing, which I said before, don't really are more hardware related and then don't fit that much into the other topics. We did cover parts of chapter 12 today, which is data structures for graphics, and I covered those parts in relation to ray tracing that are also interesting and important for projective methods, for this picking, for the game developers here, which I think is the majority. And also we covered a couple of things that are not in the book, advanced graphics methods like radiosity, shadows, and some other clipping algorithms. And we didn't go into the graphics, the hardware details or the actual graphics programming in the course, but you did a lot of this in the practicals. So I think if you have done the practicals all and have done it well, you learned much more than if you would we would have covered this small chapter 18 that is in the book. So this is basically it for the course, but of course this is not the end. There is more about graphics, so since people are often asking me what other things can I do if I like this, or what do I have to avoid if I don't like it. These are all the courses that are somehow related to graphics. So for the bachelor, the first three, I actually only listed them because the graphics course is officially mandatory to take those courses, although the first one is not really related to graphics, but in that course you need a lot of linear algebra. So if you like the mathematical part of it, I think you will probably also enjoy the first course here. The courses that are mostly related to graphics, you remember at the beginning I said most important methods or areas we cover in 3D graphics are modeling, rendering, and animation. And I also said we're mostly covering the rendering here. So if you're interested more in modeling, I recommend this course on three-dimensional modeling. I'm not pronouncing it in Dutch. It's which is it's both a master and a bachelor course. It's taught by my colleague Robbie Tan, who I'm also sharing an office with. And in animation, there is a master course on computer animation. It's a new course that was established last year. There will also be for the master students course on advanced graphics. At least it is scheduled now for the next academic year. It is not 100% sure yet if it will take place because the plan is to hire a new person, a new professor for computer graphics, and he is supposed or she is supposed to give the course. And it's not clear if he or she will be here in time. And if not, then it's also not clear what will happen if someone else will teach it or if they will just reschedule it. But it is, I've seen it, it is already in the plan, I think, for the third quarter. So advanced graphics, of course. And then there are all these other fields that are kind of related to graphics. So, for example, if you like graphics, then you usually also like computer vision or image processing, which is this bachelor course here, and the computer vision course in the master. Again, this is taught by Robbie Tan. If you like more the algorithmic part of the course, then this geometric algorithms course might be interesting for you. It's not really related to graphics, but it has a lot of these algorithms, like scanline algorithm is something that is often also interesting in relation to geometric algorithms. And if you like more the application-oriented side, you might be interested in more HCI techniques and interaction. And for that, there is actually this interaction technology course at the bachelor level, and I forgot my own course, which is the multimodal interaction, which is a master course. And these courses are not really graphics courses, but for example, things like virtual reality is also partly covered in that courses. And that way, usually people who like graphics sometimes also enjoy these courses. Good, and of course there was also option to do projects and for master thesis experimentation project, for master students experimentation projects and master thesis, but for bachelor students I think you could do Capita Selecta. So if you're interested in that, I would recommend approach people who are teaching these courses, because like I said, we don't have a graphics professor here yet, but a lot of people say always, yeah, I like the course, I'm interested in more project work in that area. Then I always recommend contact someone of the people who are teaching these courses. Good. All right, but of course that only works if you have done this course very well, which is why I have a few more comments on the remaining things of the course. Practicals deadline is Thursday. Remember, there are extra teaching sessions. There's extra sessions where teaching assistants are present. But also remember, we only have a very small room for that. So if you all come on Thursday, it will be very crowded. You might not get a space. So bring your laptop if you have questions, and don't be prepared that there are 2 teaching assistants on Thursday, but there might be more than 2 groups there. So you might not get that much attention as you want. Nevertheless, I think it's better than what we usually have, which is just a 2-hour time slot assigned per group. So I think the approach that we use with this having the whole room reserved for the whole week works actually much better and works in your favor, but you have to be prepared that before the deadline it's a little busy there. Good. We will again do random code checks, and because of the summer vacation, we will do this directly after the exam. You might not have your grades by then, but since the code check is not to make your grade or to verify your grade, but just to make sure that you really did, what you're claiming you do, it doesn't really matter. So I will send out emails sometime before the exam, and then if you get this email, you are supposed to show up after the exam. For the tutorials, there is a small change I want to make. It's always the problem at the end of the course, depending on how many holidays we have and what special events are and how soon or late they schedule the exam. And this year I realized that the day between the last tutorial and the exam is the time is very short, which is why I want to put the solutions of the tutorial online already today. So the people who want to start preparing for the exam now, I don't want to hold them back. I want to encourage you to do so, which is why I put the solutions online today. If you follow usually the Thursday tutorial, of course, just don't look at them, or look at them, and then on Thursday you can ask all questions to the whole course, to all the other stuff that is covered in the exam as well. So use this as an opportunity. Of course, Thursday we only have the small room, and there's no way for me to change that now. But also it's the same time as the deadline for the practice, so I think it should work out. But just as a reminder, Peter will be there and will be happy to answer your questions. Also other questions related to everything that is covered by the exam. And of course, remember there is also this advanced graphics talk, which is not part of the course, but like I said, if you like the course, I'm pretty sure you will like that course as well, that talk as well, maybe even more. Good. Final exam, just quickly, next Tuesday, 9 to 12. Again, we have a 2-hour exam, but I scheduled 3 hours because with 200 people, it's better to have a little buffer. But that also means if you're running a little late, if you miss your bus or so, make sure you come anyhow, because usually I can let you join later. The official rule is half an hour. I'm usually a little more flexible unless if someone already left the room after half an hour, of course, then I cannot allow anyone more to join. But it's even if you missed the bus, it's good to try it and show up, even if it's a little later. But the best thing is, of course, if you come in time, because then you have most of the time for the exercises, which we'll cover now, lectures number 6 to 12 and tutorials from the second part. So be careful, the last tutorial was split in 2 parts because we had this with the lecture today. It also has to cover the lecture today. And of course, all the necessary knowledge from the midterm exam. I will not make an explicit question, write down the implicit equation of a plane, but you might need to write down the implicit equation of a plane as part of one of the other algorithms that we covered in the second part. Other than that, there are the same conditions for the midterm exam. For those unfortunate under you who don't make it, the retakes will be August 16. Be careful this time, the retakes conditions have changed compared to last year. Last year they were, I think, a little nicer to you because I decided to make it that way. Now the administration encouraged me to stick to the general rules, which, yeah. Well, it's just one retake exam now that covers the whole course and replaces the lower of your original grades. So be careful with that, especially for the students from last year, that you do not rely on last year's information. I don't want to say much about the retakes because I want to encourage you all to not to pass the course in the first round. I will put information then on the website. If you have questions about this, always just send me an email or drop by and ask me. Good. Are there any questions about this? No? Because then I'm basically done with it. So I hope you enjoyed the course, and I hope to see none of you in August. Good.